Okay, so this is the third and final video regarding electrolysis in terms of the new content. And the first video was about electrolysis in general. So the first video was about electrolysis in general, and we focused in particular on molten compounds. And the second video focused exclusively on the extraction of aluminium using electrolysis. And then this final video is on aqueous electrolysis. So if you remember right, in that first video, we said that we needed our ionic compounds to be either molten or dissolved, i.e. aqueous in solution, for us to actually be able to do electrolysis. So we're going to start again by sort of recapping and thinking about our ionic compounds and thinking about the ions that are present and thinking about their formulae. So sort of building on or reminding us of stuff that we've done many times before. So we're just going to start by just going through these different compounds and thinking about what ions are present in each, and then we'll think about what the overall formula would be. So we've got magnesium chloride. So how could we know what ions were present there? Well, firstly, let's just remind ourselves that metals always form positive ions and non-metals always form negatively charged ions if we're talking about ionic compounds. And one way that we can recognize that there's an ionic compound is to see that there is a metal and a non-metal. And so our appreciation of the periodic table is absolutely fundamental to this. So magnesium is in group 2, so that means it has 2 electrons on its outer shell. And if it's to have a full outer shell, which is the whole point of becoming an ion, then it would need to lose those 2 electrons, so it would become a magnesium 2+ ion. And if we think about chloride, chloride is, well, chlorine is in group 7, so when it becomes ionic, it becomes, we call it chloride. It's in group 7, it's got 7 electrons on its outer shell. It would need 1 more to have a full outer shell with 8 electrons, so that's going to be a 1- charge. Sodium is in group 1, so it's going to form a 1+ ion. And bromine, which becomes bromide when it's ionic, is in group 7, just like chlorine, and so when that becomes an ion, that's going to gain 1 electron, and it's going to be a 1- charge. Calcium is in group 2, so it's going to be calcium 2+. Chloride we've already done, will be 1-. Aluminium is in group 3, that means it has 3 electrons on its outer shell, and it's going to lose those 3 electrons when it becomes an aluminium ion, so it's going to have a 3+ charge. Oxygen is in group 6. When it becomes an ion, it becomes oxide. We need 2 more electrons to go from 6 to 8 to have the full outer shell, so we're going to have a -2 charge. Copper 2 chloride. So copper is in that central block, the transition metals block, so it's between groups 2 and 3 on the periodic table. We can't tell from the periodic table what charge it would have, but if we have a transition metal, we get given a Roman numeral after it, and that tells us the charge. That's the Roman numeral for 2. So our copper is going to be a 2+ ion, and we've already done chloride, it's 1-. Sodium we already did, it was a group 1 metal, so it's going to be 1+, and then sulfate. So sulfate is one of those polyatomic ions that you just have to learn. There is no way you can use the periodic table to remember both its formula and its charge. You just have to learn it, right? There are only about 6 that you have to learn. So you need to learn that it's SO4 2-. Lithium group 1, so 1+. Nitrate, another one of the polyatomic ions, another one of those ones that you've got to learn. Polyatomic just means it's an ion made up of more than 1 atom. And that has a 1- charge, has the formula NO3, so NO3-. And then magnesium we've already done, group 2 metal, and sulfate we've already done, which is SO4 2-. So we can use these ions to determine the overall formula. And so what we've got to have is we've got to have a formula in which there is no overall charge. So the pluses and minuses have to cancel out. So if we look at Mg2+, we've got 2+ charges. We look at Cl-, we've got 1- charge. So we need another - charge to cancel out the positive charges. So we need a second chloride. So it's going to be MgCl2. So just, pause the video, try and determine what you think the formulae of the remaining compounds are going to be, and then we'll look at it in a second. Okay, so we've got a plus and a minus, so they cancel each other out, so it's just simply NaBr. The calcium chloride is just like our magnesium chloride. We're looking at a 2+ metal ion, and we're looking at a 1- halide ion, so it's going to be CaCl2. Aluminium oxide is probably one of the sort of harder formulae to determine. So we can't simply just double one of the ions to get them to cancel out. So what we might have to think about is multiplying them each, but obviously by a different amount. So if we multiply 3+ by 2, we'll get 6+, and if we multiply 2- by 3, we'll get 6-, and then the 6+ and the 6- will cancel out. So our formula for aluminium oxide is Al2O3. Copper 2 chloride, well, if we know that it's a copper 2+ ion, we've already seen what, the formulae for Mg2+, and the formulae with chloride with Ca2+, so it's going to be exactly the same. So it's CuCl2. Sodium sulfate, right, so we've got a 2- ion, and we've only got a 1+ ion, so we've got to have another positive charge, so we have to have 2 sodium ions for every 1 sulfate ion, so it's going to be Na2SO4. Lithium nitrate, we've got a plus and a minus, so we just stick those together, so LiNO3. And then we've got, with magnesium sulfate, we've got Mg2+ and SO4 2-, so we've got a 2+ and a 2- charge, so we just, again, stick them together, don't have to change the quantities of each, so MgSO4. Now this is just, this isn't exclusive to aqueous electrolysis, thinking about these ions and these formulae. It's a key part of a lot of the chemistry that we do, but obviously this is an occasion in which we actually use those ions when we're determining something else later. Okay, so if we had magnesium chloride, we're just going to focus on what we did in the first video, but it's a recap of what would the products be if it was molten electrolysis, because that's going to help us when we consider the products for aqueous electrolysis. So magnesium chloride, we've already said, is made up of Mg2+ ions, it's made of Cl- ions, and if we're going to do electrolysis on them, then we need to make sure that we've got a pair of electrodes, we're going to have a power supply. The bulb is just there so that we can tell that our circuit is complete. So if the bulb is lit, we know that there is a flow of charge, there is a current flowing. If you, in an exam, if they ask you to draw the apparatus or draw a diagram of the apparatus, then you must include a bulb. Okay, and then we've got when we actually turn on our power supply, and so we end up with a negatively charged electrode and a positively charged electrode, then the Mg2+ ions are going to be attracted to the negative electrode. And when they get there, we've talked about how they're discharged, which means how they return back to the fact that, sorry, that they're returning back to their elemental form. So Mg2+ is becoming Mg again. To do that, it's got to gain 2 electrons, and if a substance is gaining electrons, then that is reduction. So remember our oil rig acronym. So oxidation is loss of electrons, reduction is gain of electrons. So here our Mg2+ ions are gaining 2 electrons, so magnesium is being reduced. We can show that with a half equation. Okay, so we've got Mg2+ plus the 2 electrons becomes Mg. And then because magnesium is a metal, what we'll see or observe, and observations, if they ever ask in an exam, what would you observe? You do have to think, what would you actually see? Okay, so we would actually see solid metal form on the electrode. We would see it basically become coated with that metal. If we look at the other electrode and we look at the other ion, so Cl- ions are going to be attracted to the positively charged electrode because, like as we had with the magnesium, opposite charges attract. This time when the chloride ion gets to the positive electrode, it's going to be discharged again, but this time it's going to have to achieve that by losing an electron, or right, it's going to go from Cl minus to Cl. Only we know that chlorine exists as a diatomic molecule, so it exists as Cl2. So what we get is that each chloride ion is oxidized, so oil rig, oxidation is loss, because each ion loses one electron. And if we're to form Cl2, then we need two Cl minus ions to undergo this process so that we can form that diatomic molecule. And again, if we look at our half equation, so we know we're starting with chloride ions, we know that we're making chlorine gas, so we need two chloride ions to have the right number of chlorines on both sides, and then we balance it with electrons. We have a 2 minus charge in total on the left, and before we add the electrons we've just got a 0 charge, so these are the electrons that are being lost, right? So they are now no longer with the chlorine atoms. And because chlorine is a gas, what we'll see, or what we'll observe, is effervescence or fizzing. Okay, so and we'll notice that, we'll see that around the positive electrode. So if we were doing this as an actual practical, we would have a molten solution of magnesium chloride, and once we started the power supply, over time what we would observe is the negative electrode becoming coated with magnesium metal, and we would observe fizzing or effervescence at the negative electrodes, and we could do a test for chlorine gas, and we'd probably smell it, although that's not something to be advised. And this would be our overall reaction equation. Magnesium chloride is being broken down, so this is an example of a decomposition reaction. It's a single substance, magnesium chloride, being broken down into simpler substances or simpler parts, broken down to magnesium and chlorine, and this would be the way or a method of extracting magnesium metal from a compound. So if we think about the products of molten electrolysis, if we think about our three different ionic compounds here, we would get magnesium, we would get solid deposits of magnesium from our magnesium chloride, and we would get chlorine gas. In sodium bromide, we would get our sodium, solid deposits of sodium metal, and we would see, we would get bromine gas. Bromine actually is a liquid at room temperature, but because we're doing this to molten sodium bromide, that means we're at a very high temperature, so that any bromine that's produced would basically become gaseous straight away. If we look at our copper oxide at the end, there are two ions, copper 2 plus and oxide 2 minus ions. Our copper would be reduced to the copper metal, so we'd see solid deposits of copper metal, and our oxide ions would be oxidized to produce oxygen gas. So moving on to aqueous electrolysis, let's just remind ourselves what aqueous means. It's a state symbol, or we have the little AQ. So it means it's dissolved in water, right? So anything that's aqueous is dissolved in water, and so many reactions that happen basically within your body are taking place in water. Your body is about 70% water, so so many chemical reactions are taking place. So aqueous has become its own state symbol. Now, why would it be important for something to be aqueous, or why would we possibly dissolve it if we wanted to perform electrolysis? Well, this goes back to the structure and bonding topic that we did a while back when we looked at the different types of bonding, so ionic, covalent and metallic, and then we looked at the different structures that resulted from those bondings. And one of the things about ionic compounds was that they were giant lattices. That meant that they have a regular repeating pattern of oppositely charged ions, and when they are a solid, they are in fixed positions. They are not free to move. So as a solid, they can't conduct electricity because there is nothing to move, there is nothing to carry charge. And our sort of lattice structure would be very much like our year 7 particle model, so nice neat rows. The reason that then we need to dissolve it is because we need those ions to be free to move. We need them to be able to carry charge. We need them to be able to go to the oppositely charged electrode. So molten and dissolved ionic compounds conduct electricity. So that means, and that's because their ions are free to move, they're able to carry charge. And then we call that liquid that comprises those ions, we call it an electrolyte. Okay, and we need an electrolyte for there to be a possibility of electrolysis. Now, we may have a choice with a substance between melting it and dissolving it, and so the question might ask, well, why might we choose one or the other? So let's think about an advantage to having it as in aqueous form. Well, a massive advantage of having it in aqueous form is that we would need to use a lot less energy because we wouldn't be melting it. So if we take something that we're familiar with, if you take sodium chloride, common table salt, if we were to melt that, we would have to get its temperature up to about 950 degrees Celsius. It's very, very hot. But you know that you can just simply put it in water. Table salt will dissolve in water, and straight away the ions would be separated from each other and they would be free to move, and we could perform electrolysis. There is a caveat to this in that, which is what we're moving on to, in that we may not necessarily get the product that we wish at each electrode, but that's something for us to now explore a little bit further. Okay, so these are, again, I'm not bothering to go back and say, oh, magnesium chloride is a magnesium 2+ ion. Now, but here, let's just pay attention to the fact that one of the things that I've added is the fact that these are aqueous. Okay, so we are saying magnesium chloride dissolved in water. We are saying sodium bromide dissolved in water, and we are saying copper sulfate dissolved in water. Now, I've written the ions that we're already aware of, but actually there are going to be two more ions present. And one of the reasons is that water has a very small quantity of hydrogen ions and a very small quantity of hydroxide ions. And that is going to be exaggerated when electrolysis is performed as well. So what we've really got in our solution, or once we switch the power supply on, this is certainly the case, but actually it's the case beforehand, is that we have got 4 ions. We've got 2 positive ions and 2 chloride ions. So if they ever use the word solution in a electrolysis question, and that's what they'll do, they won't say aqueous, or they probably won't say aqueous. They will probably use the term solution. You have got to remember that as well as whatever the ions that are in the ionic compound, whatever they are, as well as those being present, you must also remember that H+ and OH- are also present. So when we switch on our circuit, when we switch on our power supply, it's not clear, or it isn't yet clear, as to what our products are going to be, what actually is going to be discharged at each electrode, because we have 2 possible positive ions that could be discharged, or 2 possible elements that could be discharged at the negative electrode, and 2 that could be discharged at the positive electrode. So we're going to have to learn, I'm afraid, some new rules, although they're quite simple, but some new rules to decide which of these ions would actually get reduced and which of them would get oxidized. So we're going to take an example. So we're going to start with copper chloride. That's going to be our example. So we're going to remember it's aqueous. Okay. So that means if it's aqueous, we've got these are the positively charged ions we've got. We've got copper 2+ and H+. And we've got Cl- and OH-. There are negatively charged ions. So when we look at the negative electrode, and so when we look at the positive ions, it's going to be the least reactive element that is produced. Okay, so this therefore goes back to our reactivity series. That's how we're going to judge this. So there's our reactivity series. You do have to have a strong appreciation of the reactivity series. You do have to, you don't have to necessarily know it off by heart from potassium to platinum, but you need to have a very good idea of its basics, so that it's group 1 and then group 2 and then group 3 and then carbon and then the transition metals. It's useful to know that hydrogen is just above copper, and that after hydrogen really is copper, and then the sort of 3 decorative metals. In fact, all of those metals are sort of decorative metals. So the decorative metals are after hydrogen. So anyway, so when we look at our ions, we've got copper, okay, and then we've also got hydrogen. And we can see that the least reactive of those two elements is copper, and it's the least reactive that is going to be discharged at the negative electrode. So there we go, least reactive, copper. So it's the copper 2+ ions that are going to be attracted to the negative electrodes. So it's the copper ions that are going to be reduced. And then everything that's written here would have been applicable if it was a molten liquid instead. So the positive copper 2 ions are going to gain 2 electrons. They're going to be reduced, and this would be our half equation. Copper 2 ions plus 2 electrons produce copper. So the basic rule is at the negative electrode, whichever element is the least reactive on the or lowest on the reactivity series, that is what's going to be produced. Now, if we were thinking about observations, copper is a sort of pinky, salmony pinky color, and what we would observe over time is we would observe this negative electrode being coated, quite clearly coated with copper metal. So we would get those, we would see those solid deposits of copper around the negative electrode. We would witness that, and we'd probably see it a lot more easily in an aqueous solution than we would in a molten solution. Now, what about the negative ions? So this is a different rule, but again, it's quite simple. You just have to remember it. Basically, if one of the negative ions is a halide, so that means the element would be a halogen, so fluorine, chlorine, bromine, iodine, then the halogen will be what's produced. It will be the halide that's discharged, and what you will see is that given that all of those halogens that you're likely to get are going to be gases, gaseous, iodine perhaps not, but still, I don't remember iodine ever coming up in the GCSE. You should see effervescence, right? You should see bubbles. If, however, the negative ion is anything except a halide, so it could be hydroxide, it could be sulfate, it could be nitrate, it could be any of those polyatomic ions, then what actually happens is the hydroxide is discharged, but what's actually produced is oxygen gas. So again, you will see effervescence. So in both of these cases, you will see effervescence. And so there's a topic in year 11 in which we would where we look at the tests for common substances, and we would learn about a test that would distinguish between halogen being produced, chlorine being produced, and oxygen being produced. So we could do a test certainly for oxygen. So in this one, we know that it's chloride. Okay, so we know that therefore it's chlorine, and we know that it's in group 7, so we know it's a halogen. So it would be the chloride ion that was discharged at the positive electrodes. And so what we would observe is, or at least before we observed it, what would happen is that each chloride ion would be oxidized, and for every 2 chloride ions, each losing 1 electron, we would form chlorine gas. So there's our half equation, and so we would see that effervescence at the positive electrode. So we're going to use sodium sulfate as another example. So we know that our ions that are going to be present, remember these are aqueous solutions, so we're going to have the sodium plus ion and the H plus ion. We're going to have the sulfate ion and the hydroxide ion. Our first rule is we look at the positive ions and we look at which of those elements would be the least reactive. So we look at our reactivity series, and we've got sodium present and we've got hydrogen present, and clearly hydrogen is less reactive than sodium. So that would mean it would be the hydrogen that was discharged at the negative electrode. So whichever is the least reactive of the positively charged elements, or the ions, but you know, the element that has become that ion, that is what gets discharged. So one thing to remember is that hydrogen is also a diatomic molecule. I say also, I mean like the chlorine earlier. That means we need two H plus ions to each gain 1 electron. So two H plus ions gain 2 electrons in total, and then we form our hydrogen gas, and we would observe effervescence because we have a gas being produced. Because don't forget, this is happening in a liquid, or sorry, it's happening in a solution, and as it's happening in a solution, we would see the bubbles of gas forming on this electrode in that solution, and we would see the gas being produced. Looking at the other side, we've got sulfate and hydroxide. So remember, our rule was if there's a halide, that's what will be discharged, and if there isn't a halide, it'll be oxygen gas that's produced. Well, we've got sulfate and we've got hydroxide, so we don't have any halide. We don't have fluorine, chlorine, bromine or iodine, so we don't have anything in group 7 present. Neither of those are, so that means what we actually get produced is oxygen. Now this is a tricky half equation, and I think probably actually the simplest thing to do is to try and memorize it. It really would be considered a very high grade question, I should think, in an exam. It's tricky to work out from scratch. I'm afraid if you want to, the thing is really just to learn this. So 4 hydroxide ions become 2 water molecules and we get oxygen gas. And because we've had 4 hydroxide ions, so 4 1- charges, and we don't have any overall charge with oxygen and water, we have to make sure that we have 4 electrons on the right hand side to balance the charge. And we would observe effervescence because oxygen gas, was being produced, so we would see bubbles. So your turn to have a go. Sodium chloride. So sodium chloride is also known as brine. So sometimes if you buy cans of tuna or jars of olives or whatever, they quite often say that they're in brine, and that basically means salt water. So we're talking about an aqueous solution of sodium chloride here. So I want you to just pause the video. I want you to think about what ions would be present in this aqueous solution. Then I want you to think about the rules and think about what would actually be discharged at the negative electrode, what would actually be discharged at the positive electrode, and then we'll see if you're right. So if you could just pause the video, that would be great. Okay, so we've got sodium plus, Na plus, and we've got H plus as our positive ions. Just like on the previous example, there's sodium there, there's hydrogen. The least reactive is the one that's discharged, so hydrogen is the least reactive, so hydrogen would be discharged. Okay, so we would get hydrogen gas. On the other side, we've got chloride ions and hydroxide ions. Chloride ion is a halide ion, so we would get chlorine gas produced. So there we go, there's our example. So our overall reaction would be sodium chloride, then we would get hydrogen being produced at the negative electrode, we would get chlorine produced at the positive electrode, and we would have also, and this is also a useful product, we would have sodium hydroxide because we would have the Na plus and the OH minus left behind. And this is a very valuable example of electrolysis because all of these products are extremely useful. So hydrogen can be used as a fuel, Chlorine can be used to disinfect swimming pools, but basically is used in a variety of disinfectants. And sodium hydroxide is used to make soap. So all of those products. So we take something very simple or seemingly simple like sodium chloride. We perform electrolysis of an aqueous solution containing sodium chloride, and we actually get 3 very useful products. Okay, so that was the final video on electrolysis. I will do another which looks at exam questions, so it applies the knowledge. But if you have any queries, please let me know.